Hey Calculus class! Today we are going to learn topic 32, properties of the definite integral. So just like when we did derivatives, we had certain properties. Well, with the definite integral, we also have properties. Alright, so for each property, I'm going to have the property on the left-hand side, and there's going to be an example for that property on the right-hand side. So suppose that C is a constant and F and G are continuous and differentiable. And for our example, we're going to use the integral from 1 to 3 of f of x dx equals 17. So that means that the area underneath f of x between 1 and 3 is 17. And the integral from 1 to 3 of g of x dx is 26. So the first property is what we call the reverse limit. What this says is that if we have an integral from a to b of f of x dx, then we can say if we multiply by a negative, it flips the limits. So instead of from a to b, that means we have from b to a. And what this will look like is if we have the integral from 1 to 3, or 3 to 1, sorry, of f of x dx. And it will look something like this. So then, in order for this to work, you would have to multiply by a negative. The next one is the zero rule. So the zero rule says that if you have the integral from a to a of f of x dx, that equals 0. So if we look at the function f of x from 2 to 2, what that just means graphically is that all I'm looking at is when x equals 2, and there's no area for me to find. So there's no area underneath the curve if you're just looking at one specific point. The third one is the constant rule. The constant rule says is if you're going the integral from a to b of some constant dx. So we're going to first look at the example. So if we look from 1 to 3 of 5 dx, graphically that means you have a horizontal line at 5. And we're going from 1 to 3. So if we wanted to calculate the area underneath this horizontal line, notice it's just a rectangle. We know how to calculate the area of a rectangle, right? And that's base times height. So in this case, we would have the height is 5 times the base, which is actually b minus a, and it comes out to be 10. So that means the general rule for constant is that it's your height, which is your constant, times your base, which would be b minus a. The next one is called the constant multiple rule. This one says if you have the integral from a to b of some constant multiple times your function in the integrand, then you can pull out the multiple constant because it doesn't rely upon the x at all. So you would evaluate the integral first and then multiply by your constant. So for example, if we have 2 times f of x dx, all that means is I can pull the 2 out first and evaluate the integral from 1 to 3 first. Before we actually do this, I wanted us to look at this graphically. So what this means is the f of x dx curve is the green curve. When I multiply it by 2, that means it doubles my area. So that means I know that this area, the green area, is 17. So to get the total area underneath the red curve, then I would get 2 times 17, which equals 34. The next rule is the addition rule. This says that if you have the integral from a to b of two functions being added together, then you can split them up and take the integral of the first function and then the integral of the second function and then add them together. So for our example, if we have the integral from 1 to 3 of f of x plus g of x dx, I can split them up. And graphically, what this means is the green curve is my f of x area. The blue curve is the area for g of x, and the red curve is the sum of these two areas. So I know that this is 17, this is 26, so that means the area underneath the red curve is 43. The subtraction rule. Same idea as the addition rule. So you have two functions subtracting. You can split them up and take the integral of each of them separately. So for our example, we'll subtract f of x and g of x. And graphically what this means is that the green curve is still f of x, the blue curve is still the area underneath g of x. So to get the area of the red curve, which is the difference of these two areas, I would then do 17 minus 26, which gives me -9. And I know we cannot have negative area. What this negative area means is that's it's just below the x-axis. The next property is the interval additivity property. What this says is if you have an integral from a to b of f of x dx, you can split up the interval if you let there be some other value in that interval, and we're saying c, so that you can evaluate the first part of that interval, then the second part of that interval, and add it up. So, for our example, if we let the integral from 1 to 3 of f of x equals 17, and let's also let the integral from 2 to 3 of f of x equals 12. We want to find the integral from 1 to 2 of f of x dx. So, what this means graphically is that this total area from A to B is 17. And the area from 2 to 3, or C, is 12. We need to find this extra little area. So to do that, if we were to set up an equation similar to what we have in the property, we have the total area equal to the sum of each of the little pieces of the area. Well, I know that this is 17, and I know that this area is 12, and I want to find the area from 1 to 2. So basically, I'm just going to take my total area and subtract 12 from it to give me an area of 5. The inequality property. This says that if f of x is greater than or equal to 0 for x being between a and b, then we can say that the integral from a to b of f of x dx is greater than or equal to 0. So this property basically says that all areas are positive when the curve is above the x-axis. That's all this says. When the function is above the x-axis, the area is positive. The dominance property. This says if f of x is greater than or equal to g of x, for x being between a and b, then that means that the area underneath f of x has to be greater than the area underneath g of x. So let g of x be greater than f of x. So notice how I'm switching it. That's fine. All these function names mean is you just have whichever function's bigger between the two functions, that area of that function has to be bigger. And I'm going to let the area of from 1 to 3 of f of x dx equals 17, and the area from 1 to 3 of g of x dx equals 26. And what this looks graphically, the green area is your f of x from 1 to 3, okay? And the area from g of x, which is 26, is the blue curve. And notice that it makes sense for the area underneath the larger curve to be greater because it is above f of x. So therefore I can conclude that the area from 1 to 3 of g of x dx is greater than or equal to the area from 1 to 3 of f of x dx. And of course you can see that 26 is bigger than or equal to 17. The next property, the min-max inequality. What this says is if you let little m be less than or equal to f of x, which is less than or equal to big M, for x being between a and b, then we say that the area underneath f of x from a to b has to be bigger than the area under little m times b minus a, but smaller than the area underneath big M times b minus a. So what does that mean? All right. So little m is our minimum value of your curve, okay, on that interval. So in this case, the minimum value on my curve is going to be at a. Then the big M stands for my maximum y value on the curve. Yes, in this case, it's b. It's not always the endpoints. So what this means is that if I was to find the area underneath the rectangle formed, if I was to draw a line, a horizontal line, where the minimum is, I would create a rectangle. This area of this rectangle has to be smaller than the area underneath the curve. And as you can see in the picture, the green area, it's apparent that that's more area than this little rectangle. And then what this also says is that if I was to take the area formed by a rectangle of a horizontal line where the maximum is, so this big darker gray rectangle, the area underneath the curve, so the green area, would have to be smaller than the area of the big rectangle formed by the maximum. So the biggest things you have to keep in mind is that little m is the absolute min and that big M is the absolute max. And in this example, big M equals 20 and little m equals 2. So when I set this up, I am saying that the area under f of x from 1 to 3 has to be between the area of the little rectangle, which is 4, and the area of the big rectangle, which is 40. And as we can see, 17 is between 4 and 40. And just for your purposes in your book calls this property 8. So if they ever ask you to use property 8, they're talking about this property. All right, now we're going to talk about net area. So if f of x is greater than or equal to 0, that is, the graph lies above the x-axis from a to b, the integral from a to b of f of x dx gives the area under the curve. If the graph of f of x lies both above and below the x-axis, then the definite integral gives what's called the net area. The area above the x-axis subtracted by the area below the x-axis. So what that means, if we were to look at that, any area above the x-axis is considered positive area. Any area below the x-axis is considered negative area. So what that means is that you're going to take the area above minus the area below. All right, let's go ahead and do some examples. So suppose that f is an integrable function and that the integral from 0 to 1 of f of x dx equals 2, the integral from 0 to 2 of f of x dx equals 1, and the integral from 2 to 4 of f of x dx equals 7. So for part A, we want to find the area under f of x from 0 to 4. So notice that I do not have anything that goes directly from 0 to 4, but I do have pieces that will go from 0 to 4. Notice this piece goes from 0 to 2, and this piece goes from 2 to 4. So that means we have to use that property where we can take two of the smaller pieces of area and add them together to give me the larger area. So that means I have 1 plus 7. So the area would be 8. Now to find from the integral from 1 to 0 of f of x dx. And I know this is kind of weird, but whenever you see the limits flipped, if you want to flip them back normally, you multiply by a negative. So notice here that we know from 0 to 1, that equals 2. So in order for me to flip it, I have to multiply by a negative. So that means my answer is -2. Now if I want to find the area from 1 to 2, notice I do not have 1 to 2, but I do have 0 to 2, and I have 0 to 1. So I'm going to use that same property that I used in part A, take the total area, which is from 0 to 2, and add up, and that equals the area from 0 to 1 and from 1 to 2. Well, I know from 0 to 2, that's 1. From 0 to 1, that's 2. So I'm going to find the area from 1 to 2. So that means I'm going to subtract 2 from 1. So my area is -1. All right, another type of example you're going to see is ones that say evaluate the integral from -3 to 3 of some function, in this case the square root of 9 minus x squared dx, geometrically. And what this means geometrically is that if you were to actually graph this function, you'll notice that it's actually some geometric shape that you already know the area formula for. And you should notice that this is the area of, this is the function for a semicircle with a radius of 3. So if you were to graph the top half of a circle with the radius of 3, you get the following graph. Now, can we find the area of a semicircle? Yes, we can. We know that the area of a semicircle is pi r squared divided by 2. And we know that the radius is 3. So therefore, I'm going to plug it in. So that means that the area underneath this curve from -3 to 3 is pi times 9 all over 2. And you're done. All right, now let's look at something that is a little bit more AP-ish. So for this question, the graph of a function f consists of a semicircle and 2 line segments as shown below. Let g of x equal the integral from 1 to x of f of t dt. So what that means, in part A, if they want you to find g of 1, that means I'm going to plug a 1 in this function wherever I see an x. So that means I can rewrite this function as g of 1 equals the integral from 1 to 1, because there's an x up here, of f of t dt. Well, we know that there's that property, it's the constant rule, where if you're taking the area at a specific point, well, there's no area defined at a point, so your area would be 0. Now, if we were to this time do g of 3, so that means now our integral is going to be from 1 to 3. So if I come over to my graph and look to see what we have, from 1 to 3, I have a triangle that is below the curve. And can't we find the area of a triangle? Yeah. We know that the area of a triangle is base times height divided by 2. Well, in this case, the base is going to be 2 from the difference between 1 and 3, and the height is going to be -1. So that means when I do half of base times height, I'm going to get -1. Now to find g of -1. So when I plug in -1 for x, I'm going to get the integral from 1 to -1. And this is a little foreign. We don't like the limits to be out of order. So if this ever happens, you're going to want to flip the units. So in order to flip the limits, you're going to multiply by a negative. So now what I'm really going to evaluate is the negative of the integral from -1 to 1. So when I look at the graph from -1 to 1, you should notice that you don't have a semicircle, you have a quarter of a circle, right, with a radius of 2, right? Because if -1 is your center, to get to the outside, you go 2 units on either side. So I know how to find the area of a quarter circle. It would be pi r squared divided by 4. Well, the radius is 2. And so then I'm going to have negative pi 2 squared over 4, which reduces to negative pi. Another example. This time we're going to estimate the value of the integral from 0 to 2 of x cubed minus 3x plus 3 dx by using the min-max inequality. All right, so I need to find the max and min values on the function. Now, I'm not finding local maxes and mins. I am finding absolute maxes and mins, which means y values. So I can take my function. I know in order to determine a max and a min, I need to find the derivative, set the derivative equal to 0, solve for x to get, in this case, negative 1 and 1. Now, if you notice, I'm only concerned on the interval from 0 to 2. So that means x equals negative 1 isn't in my interval, so I can basically ignore it. And since I want absolute min and max, that means I have to determine which out of x equals 1 and my endpoints 0 to 2 give me the largest y and the largest and the smallest y. So I'm going to first test 0. So I'm going to plug 0 into the original function to get 3. Then I'm going to test 1 to get 1. And then I'm going to test 2 to get 5. So my absolute min is at x equals 1. And the actual minimum value is 1. And then my absolute max is at x equals 2. So the max I'm going to use is 5. So that means that little m equals 1, big M equals 5. So that means I can now set this up, and I can approximate that the area of this curve between 0 to 2 is going to be between the areas of these 2 rectangles. With the first rectangle has a height of 1 and a base of 2, and the bigger rectangle has a height of 5 and a base of 2. So that means that the area of this function from 0 to 2 has to be between 2 and 10. All right, next example. A particle moves along the y-axis with velocity given by v of t equals t times sine t squared for t greater than or equal to 0. Where is the particle after the first 2 seconds if y of 0 equals 3? So we know that the total distance traveled equals where you start plus the distance traveled during the time interval. So in this case, we're starting at 3. So if you're on a number line, we are starting at 3. So that's our starting place. The distance you've traveled on that time interval is the area underneath the velocity curve from 0 to 2. For now, you're just going to use your calculator to evaluate this definite integral. We will learn the shortcut soon. So for now, all I want you to do is type this integral into your calculator, like I showed you earlier this week. And when you do that, and don't forget to add 3. And after you add 3, you get 3.82682. So that means that the particle is at position 3.82682 after 2 seconds. Well, I hope you enjoyed learning about the definite integral properties, and I will see you in class tomorrow. Have a good night.